Yeah, good morning everybody. It's my great pleasure to start my lectures today. The title, the big title of the lectures was called Applications, and this is of course too wide, so I took the liberty to define it a bit more precisely what I wanted, what will be the subject. And I will, as you will note, mainly focus on atomic clocks with cold atoms and ions, in the spirit about speaking about interaction of light and cold atoms. And I think it's fair to say that atomic clocks are the most important application in the sense that it is used for applications that go beyond the study of the interaction of the atoms and the light. And connected with it, there is a number of practical applications connected with it already, but which I'm not going to touch so much. But there is a very important scientific application because of the very high precision that can be obtained in this type of experiments. It has been a very important range of research to use these types of clocks for precision measurements and for testing foundations of physics. This is something that goes a little bit beyond the subject of the cold atoms and the light, but I think it is of really of a general interest for physics. So I will also cover it in the course of these lectures. So maybe I should introduce a little bit myself, or maybe I should introduce you. You see me, but maybe I should say a few words about my affiliation. PTB is not a university. It is here you can read the full name. It is Physikalisch-Technische Bundesanstalt. So for the non-German speaking, maybe a little bit difficult to pronounce. It is a national metrology institute. Metrology, the science of measurement, and all the countries have their national government institute that takes care of measurements on the highest level of precision for legal aspects, of course for scientific aspects. So the highest duty of these institutes and of PTB is to take care of the realization of the base units, of the SI units, of which of course the second is one. But then it also goes into all kinds of practical considerations. And so these institutes I mentioned, they exist in all the countries. And PTB is the oldest of those. It is more than 130 years old already. The British have what they call the National Physical Laboratory. In the US, it's called the NIST, National Institute of Standard and Technology. In France, it's a little bit different. It's not so centralized as one can compare to LNA institutes. And so these are the measurement institutes, and we are located. There's two locations: time and frequency. I'm in charge of the time and frequency, and we are located in Braunschweig, which is a small town between Hanover, somewhere between Hanover and Berlin. Okay, I'd like to come to the historic background of the field, and I'd like to start with a very early citation from a great scientist, from James Maxwell in 1870. He gave what we can now call an early vision of quantum metrology. If we wish to obtain standards of length, time and mass which shall be absolutely permanent, we must seek them not in the dimensions, motion or mass of the planet, but in the wavelengths, period, vibration, and the absolute mass of these imperishable, unalterable, and perfectly similar molecules. I think it's a very remarkable statement, seeing that it was done in 1870. It was just the time when people switched towards the metric system. So before the length was defined, I don't know, via the arm of the king or so. And this was the beginning of the scientific area, where just the meter was defined via the meridian of Earth. And now quite immediately, like 20 years later or so, Maxwell was saying, no, we should not do this. We should not take the dimension of the planet or the motion of the planet, but we shall take the wavelengths and period vibration of molecules. Molecules, I guess he meant equivalent also, we can say, with atoms. So this is really indeed a very modern and visionary statement. So today, in today's language, we would say the physics or the science behind this is that atomic energies are natural constants that do not depend on space and time. They are universal apart from relativistic effects, and that therefore they are very well suited to have universal measures of length and of time. This postulate is part of Einstein's equivalence principle, which is one of the foundations of relativity. And I'm going to come back to it in my third lecture, where I will speak about the tests of fundamental principles. So in fact, the measurement of time via atoms or molecules is really had really been a new concept, because the measurement of time was important in the history of mankind for centuries. And for centuries, the most stable periodic phenomenon that was available, of course, was just the rotation of the Earth. Of course, also the duration of the day, the most practical unit of time, the most of the highest practical importance for people. And so time could be measured maybe with a solar dial, and also from the solar observation it provided the historic definition of the unit of time. So the second until today is related to having a day that is divided into 24 hours, 60 minutes, and 60 seconds, going back, I think, to the Babylonians also, with the use of the system based on 12 units. The first proposal for an atomic clock, first realistic proposal, so I would say Maxwell made like the visionary proposal. The realistic practical proposal was pronounced by Isidor Rabi in 1945. And this was building on the work with atomic and molecular beams, the nuclear magnetic resonance, and very important also during World War II, the development of microwave electronics that was important for radar. And for this work, Rabi had won in 1944 the Nobel Prize in Physics. And then in the beginning of 45, he was invited for a big evening lecture by the American Physical Society. He gave this in New York, and in this lecture, which was then actually taken up by the New York Times, I think it was even the front page maybe, he made this proposal for an atomic clock, and this is how it appeared in the newspaper: cosmic pendulum for clock plant. Radio frequencies in hearts of atoms would be used in most accurate of time thesis. Design term feasible. Well, that sounds great, and indeed it was very well prepared at the time, and it was a very realistic proposal based on the physics that Rabi's group had developed. This is then there was, like, over 10 years, it was kind of a race towards building the first really operative machine. There was strong research in the US, in Britain. The British were ahead. I mentioned already, the National Physical Laboratory, that is the Metrology Institute. Louis Essen and Jack Perry with the first operative cesium clock in 1955. So you see they dressed up for the occasion, and they showed the operation of the clock. Here in the center you see a vacuum tube. It's about 2 meters long. Here you see some microwave waveguides, and there will be an atomic oven. There is a vacuum pump, and so on, and some coils for the compensation of magnetic field. So this was the first precise, or the first operative precise atomic clocks. This shows now a little bit on the history of timekeeping. Here you see a historic scale going back to the Renaissance time until today. And here on a logarithmic scale is plotted the daily uncertainty or discrepancy of these man-made clocks. And you see, so each unit here is a factor 1,000 improvement, and you see how dramatically even the slope of this curve is changing over time. So starting from mechanical clocks, pendulums, and mechanical clocks that are on the order of 1 second per day uncertainty until about 1900, and then came quartz clocks, piezoelectric oscillations in quartz crystals that are below a millisecond per day. This crossed one important border, which is marked here. This area of about 1 millisecond per day is marked here as the irregularities in the Earth's rotation. So the Earth is not a perfect solid body, but there is many moving masses inside the Earth. There's a liquid layers of the Earth outside the biosphere. The water is moving over the year. So the moment of inertia of Earth is not constant, and that's why the rotation rate of Earth is not constant. So it varies, like on this scale of a millisecond per day. This means actually, this is a point already where we see that Maxwell was right, that we have a benefit in going away from the astronomical observations by going to something different. Quartz clocks, and then starting in the 1950s, the atomic clocks with the microwaves starting at about a few microseconds per day, then going up to the nanosecond per day. And here now today optical clocks going further to like 10 to the minus 18 or so relative uncertainty. And all these advance I've marked is correlated with an increase of the operating frequency of the clocks. So the clocks are ticking faster and faster. And this is what I've marked here. So mechanical clocks, of course, 1 per second. Quartz clocks, 10 kilohertz, microwave clocks, gigahertz range, and optical clocks 10 to the 15 hertz. So the clock that ticks faster allows to separate time into smaller slices, to measure, to count a higher number of oscillations in a given time interval, and that's why it also provides a higher accuracy. I will explain it in a more physical picture. So this is the historical development behind the enormous precision that we have. In consequence, it makes now today the second is now realized with an uncertainty of about 2 parts in 10 to the minus 16, a relative uncertainty, and this is unique, or this is outstandingly better than all the other base units of the SI system, which have uncertainties in the range of 10 to the minus 11 for the meter, which is an optical interferometric measurement, and then the very important, of course, practically very important electrical and mechanical units, the kilogram, the ampere, in the range of 10 to the minus 8. And so time intervals and frequencies are the most precisely measurable quantities at all in physics. You have heard Jörg Wallraben discussed it, mentioned it yesterday, that there was a redefinition of the SI system taking place this year. So with now the units being linked to fundamental constants, the most important change was, of course, for the kilogram, where until then it was linked to the prototype kilogram in Paris. And here basically the uncertainty in the realization was 0, because it was just this device was the kilogram, so there was no uncertainty. But of course there was an uncertainty in comparing the kilogram and in transferring the unit. So now it has about 10 to the minus 8, and it's now linked, the kilogram is now linked to Planck's constant. For the second, nothing has changed. It is still linked to the cesium hyperfine frequency, but somehow you may say that with this reform, the second even became a little bit more prominent in the SI system, because the second is the one unit together with a mole that is directly linked to the constant. So the constant here is the cesium frequency, 9.2 gigahertz, directly defining 1 second. But if you speak about the kilogram, for example, the unit of Planck's constant is joule second. So in order to understand what a kilogram is, you also have to know what a joule and what a second is. And that is, you have to know the definition of the second and of the meter. So from this point of view, you need the system is now somehow in an iterative setup in layers, that you have to know the second which enters into the meter, of course, via the speed of light, into the kilogram, also into the electrical units. So from this point of view, maybe it's a little bit an academic statement, but it's reassuring that the uncertainty here is so low, because it means that the uncertainty in the realization of the second will not enter into the realizations of the other units, although it is used at this point. This is a This is a very important diagram, and I will show it later to you, but I'll show it here to give a little bit the motivation. It shows the principle of the atomic clocks and all the elements that I'm going to discuss more. By the way, I will upload the slides so that you can have the slides for download also. So this shows the principle of the atomic clock. The clock principle is always, and here is now the interaction between light and atoms. There is an oscillator, a laser oscillator, and there is the atom that provides the reference. So the laser radiation induces a transition or a coherence between two levels of the atom or ion or molecule or nucleus. And then simple by Bohr's relation, so the energy difference is related into a frequency. Of course, the response of the atom has to be measured. This is really a quantum mechanical state detection, and then this outcome of this measurement has to be transferred into a signal, into an error signal that is used to steer the frequency of the laser, so that the frequency of the laser is in agreement with the atomic frequency. And then you have a closed servo system here, and you know that the laser frequency is in agreement with the atomic frequency. And then in order to have a clock, you need a clockwork, which is in this case for an optical frequency, a femtosecond frequency comb. I will also speak about it later. So to divide the optical frequency down into a frequency range that you can count and that you can base a time scale on. This is really all the important ingredients, and I will speak about all the ingredients, especially about the atomic part in much detail during these lectures. So this brings me to the outline of the lectures. So it will be 4 lectures. Here you see the 4 blocks. The first one cover quite a number of the concepts and methods that are needed, and it will take me today and tomorrow. I don't know exactly where this break will happen, but it's roughly I think the 2 days will be needed for the concepts and the methods. Starting from the basics to the understanding of why and how these very low uncertainty can be obtained. And then on Thursday, I think I will speak about these tests of fundamental principles. And for Friday, I noted this is the last day of the school, so I have reserved a special topic for which I think is fun and interesting. That is the discussion of how to transfer these methods of excitation from an atom to a nucleus. And that is something that I think is very interesting in physical terms, and also promising to eventually produce what one may call a nuclear clock. Okay, I will start with the introduction of the cesium clocks. The cesium clocks is not about light and atoms. It's about microwave and atoms. But I'd like to introduce them because a number of the basic ideas, of course, were developed in cesium already. It is practically important. It is a realization of the SI units, and that's why I take it to introduce some of the concepts. I will mainly, just a note, I will mainly go with the slides. You will see very few equations in my lectures. You will see many diagrams, and which I think is just better on the slides. And if I were to draw it by hand, you will recognize it easier. If you feel that I'm going too fast, please ask questions. So then I'm happy to explain things. Microwave atomic clocks are all relying on single atom hyperfine ground state hyperfine structure. So the simplest atom could be hydrogen. You have a proton which has a nuclear spin. You have an electron that has a spin, and these two spin may couple either parallel or antiparallel. And these two states, of course, are separated by an energy interval, which is the ground state hyperfine structure for hydrogen 1s. It's given here in electron volt, micro electron volt, or You may remember these numbers, 1.4 gigahertz or 21 centimeter wavelengths of the radiation. The transition between the two states with the nuclear spin and the electron spin aligned. Why is it useful for a clock? It is something that is deep in the atom, in the interaction of the 1s electron with the, what is my computer trying to do here? Interesting. Oops, sorry. So it is a process between the inner electron and the nucleus. So it's relatively unperturbed. It's deep in the atom. It's a microwave frequency. So it is the transition rate here is very slow. It's a very weak transition, a magnetic dipole transition. It's very long-lived. So there is no issue of a natural line width in this clock, and it's so it is a very stable. It is a very stable frequency reference. You can see, yeah, here it's given in eV and in gigahertz of frequency. In any kind of microwave atomic clock, it requires a state selection. So if you take the atoms, normally you see here the difference, microelectron volt. So at room temperature, these two levels would be equally populated. So one has to start with a state selection. Of course, today we do to create a non-thermal population distribution. Of course, today we do it by lasers, by optical pumping, by hyperfine pumping. But in the 1950s, there was an even simpler, very simple method, which is magnetic state selection, or we can say spatial state selection. So there is this ensemble of the atoms, both states equally populated. You can see the dark and the light circles here, and it is passed through a inhomogeneous magnetic field, and the inhomogeneous magnetic field splits the two states spatially. It produces a force on the atomic beam, and the atoms are spatially separated. How does it work? We have to look at the level scheme of this atom in the magnetic field. So this is the hyperfine splitting. Now I have selected quantum numbers 3 and 4 for cesium, not for hydrogen, but for cesium. And here is a magnetic field, B in Tesla. And we see at field 0, where finally we want to operate the clock. We have all the levels, all the Zeeman sublevels are degenerate, and we have the hyperfine splitting. And here we want to operate the clock. We want to operate the clock at field 0, at magnetic field 0. And in addition, in order to make it insensitive to fluctuations of the magnetic field, we want to operate it on the M0 sublevels. The ones that do not show a linear Zeeman effect, but the lines, it's hard to see here, but the lines that start here horizontally out from this diagram, so that for small fields, the frequency has no linear dependence on the magnetic field. But you know there is a transition from the Zeeman, what's called the Zeeman regime, to the Paschen-Buck regime, where the external field is on the order of a Tesla. That is, it is as big as the field from the nucleus inside, and it means that the external field now changes the coupling between the electron and the nucleus. It somehow decouples them, and the electron couples to the outer field more strongly. And you can see that the lines are bending. You have the two manifolds which are originating from the orientation of the electron in the outside field, and then these have a substructure that is related to the nuclear orientation. And here you see now that you have some lines that go up in energy with a magnetic field. So these are what can be called magnetic low field seekers. So they would, in order to lower their energy, they would go to the low magnetic field. And for these, it's opposite. Their energy goes down with the magnetic field, so they are what we call high field seekers. They are lowering their energy by going to the high magnetic field. And since there is only two manifolds, the zero lines here have to separate. So one of the zero levels is on the downside manifold and one is on the upside manifold. That is, if we go to the strong field, we can separate. One of these states is a low field seeker, the other one is a high field seeker. And that's what's done with this atomic beam. One enters a lens, a magnetic lens. Here, for example, a hexapole can be built out of permanent magnets. And you see it's arranged like this, that the total magnetic field is minimum at the center, and then it increases radially outside between the poles. And it means that such a thing will act as a lens, as a focusing length for those atoms that are attracted by the low field. That is for the low field seekers. It will act as a focusing lens for the low field seekers and the defocusing lens for the high field seekers. And that's how the atoms can be separated. So in this graph, it is not a lens here. It is simply like in a dipole, an inhomogeneous dipole, like in the Stern-Gerlach setup. Okay, now we have a state-selected beam of atoms. Now we bring it into interaction with a microwave. This is shown here just as a box with a microwave cavity. There is a small antenna that can be used to feed in the signal. And then we have shown here roughly the two conditions. Resonance condition not fulfilled. The atoms are entering the state. This box, they do not change their state. They are deflected again. Behind the microwave cavity, there is a second of these selection sections. Atoms are deflected in this way, not changing the state, but if there is a resonance condition fulfilled, atoms are changing state and then they are deflected the other way, and one may put a detector here to measure the flux of atoms. So this is how this is the basis of Rabi's proposal from 1945, and this is what the British realized for their cesium clock. Why did they use cesium? So from the 1955 perspective, when this was built, it had a number of important, mainly technical advantages. So cesium is like the one electron atom, the alkali atom, but it is a metal. It is easy to evaporate at around 100 Celsius already. It will evaporate. It is easy to detect. Cesium atom, if it impinges on a hot metal, it will ionize. It will give away the valence electron. It will ionize. So one can measure the flux of cesium as an electric current on a hot metal. There is only one naturally occurring isotope, cesium-133. So you can go to the chemistry shop, buy 5 grams of cesium for 50 euro or so, and it's isotopically pure. So all the atoms, it is not so important, but it is an advantage for the clock that all the atoms inside have the same nuclear structure, the same hyperfine structure. If you would use rubidium, you would have 2 isotopes and so on. That's different for the other ones. And also maybe more important, even if the frequency, the hyperfine splitting frequency is relatively high. Hydrogen was 1.4 gigahertz. Here it's 9.2 gigahertz. Higher frequency, I mentioned already, gives higher stability. And of course, a challenge, you have to produce a coherent microwave, but all these electronics like the sources, mixers, counters for this frequency were already available in the 1950s. So that's why cesium was a good idea. This is how such a cesium clock is built and looks today. You see the elements, an oven, the first state selection, the microwave interaction zone, the second detection, and the hot wire detector. This is how it looks in practice. This is a device that was developed by the Hewlett-Packard company in the 1980s or so, and which you can buy for still today from a company has a different name, but you can still buy this type of clock. It's about 50,000 euros or so. So okay, you better ask your institute if you need one, but then you can carry it to your lab and you have a realization of the SI second in your lab with an uncertainty of about 10 to the minus 13. You don't see so much in this picture. You see some, we opened here, we cut open, this is the one that ran out of cesium, it did not work anymore. We cut open the magnetic shielding. You can see here, here is the cesium source. You see the blue color, this is cesium, I think hydroxide or so. It reacts with air when it's open. And this is the microwave region here where there is the interaction at the detector here. In comparison to the things I've shown, there's one difference here. This is not just a box, but it is what is called a Ramsey cavity, and this is another very important ingredient of the clock. Right. So I should introduce the ideas of Rabi and Ramsey excitation, named after the people. I've shown you the picture of Isidore Rabi already. He was a pioneer of the magnetic resonance, the first experiment and so on, and you know the Rabi frequency. And here this name is used just for a pulsed excitation of an atomic two-level system, and just excited with a single rectangular pulse. So that would be the situation if you have an atomic beam, and the atomic beam is flying through a box-like cavity, then it would basically see a rectangular pulse. And you know, there is the optical Bloch equations in the regime of, these can easily be solved. And in the regime of lower excitation, this is a simple result for this excitation profile. It is basically the sinus x over x of the detuning squared. You get this shape with the maximum and the adjacent sidebands. The expression here more general is just so chi is here the Rabi frequency, delta is the detuning. It's basically the Fourier, the excitation probability after the pulse is basically the quadratic Fourier transform of the time profile of the pulse. And Ramsey's idea was not to use a single pulse, but to use two pulses. You may say it's not a big deal, but it is in fact very, very important. Without this, the clock would not work. So there is. Let's look a little bit at the mass here, which is simple. So there is one pulse, there is a dark period, and there is a second pulse. So it means that here the Fourier transform is a simple exercise. So there is the single pulse produces the envelope of the spectral pattern. You can see the expression here. But now there is a term coming from the interaction between the two pulses, and there is an additional term which is a cosine square, again of the detuning, delta the detuning. But now we have the time that enters here is not the small tau, but it is a capital T, the dark time between the pulses, which is much larger, much longer, of course, than the duration of the pulses. So it means that this cosine square term here leads to the fast oscillations that you have here. And so if you zoom in, if you want to zoom in on the center here, you have a much steeper slope across close to this maximum than you have here. So this is really practically a very important advantage. It is important. I should maybe even copy this equation. It's for cosine square delta t times sine square delta tau over 2 times chi square over delta square. So why is it so important? The line width here is determined by the duration of the pulse. So if you want to have a narrow line width, the pulse has to be longer. Simple Fourier relation. You want to measure precisely, you need a longer time. So from this point of view, you would like to make this small, for Rabi excitation, you would like to make this tau as long as possible. If you have an atomic beam, it means you have to make the box very big. But now comes the practical problems, because if you the cesium wavelengths is 3 centimeters, 9 gigahertz, 3 centimeters. So one wavelength is 3 centimeters. But if you would like, you've seen, I've showed you the picture of the British clock. It was 1 meter long. So if you would have a 1 meter box for these 3 centimeter wavelengths, it would be very, very difficult to control the phase of this microwave inside this resonator. You would have to need a very stable phase front for all the atoms that covers how much, 30, 40 wavelengths. So that's very practically difficult. And also, you would not know where during this passage the excitation would take place. So if you, for example, if you have slight variations of the magnetic field over this bigger box, this would lead to a broadening of the line. And these two problems are solved with Ramsey method, because you can see it better here. So now, instead of the big box, you have a waveguide where this microwave is fed in, and then the waveguide is U-shaped. It separates into the two regions. There is a first interaction here, then the atoms are flying through the field region, and then there is a second interaction. And you solve both problems that I've mentioned at once. So first of all, you can have a waveguide which is matched to the wavelengths, so you can much better control the phase and the wavefront. And also, all things that are happening here and that may otherwise lead to a broadening of the line, now these are averaged, because the atom is flying in the dark. You're not exciting the atom, but you're just maintaining a coherence of the atom. So everything that perturbs the atom here is averaged, and it will not lead to a broadening. And that's why Ramsey's method is so important. You may say, okay, 2 pulses instead of 1. It sounds simple, but it is really the basis of the clock and of many, many spectroscopy methods. And Ramsey duly won the Nobel Prize for this in 1989. So it's actually, Ramsey method is one of the take-home concepts from this lecture that you should remember. Ramsey was a very modest scientist, and so everybody was speaking of the Ramsey method. He himself spoke of the method of separated oscillatory fields. So that's the more technical description of what is done. Yes, please.
Is there actually a velocity selection before?
It could be. Yes, I will show you. So in this type of clock, there is not. It is basically not. So this is really just a thermal beam. But I will show you in 2 slides. It is an important criterion. Yes. So I'm introducing it here with a beam. It is intuitive, but of course also with cold atoms, we are now of course always using Ramsey methods. If the atom is localized, you don't have a beam, then the Ramsey method just means that you apply 2 pulses in temporal sequence from the laser or microwave source, and then you can have more degrees of freedom. You may apply more pulses. You may do things in between. Right. This is what I told you already. There is an additional small advantage. The central line is a bit narrower, so for the total interaction time, the Ramsey resonance is about 2 times narrower than the Rabi for the same interaction, so a factor 2 gain. This is because there is these cosine squares. There is delta t instead of delta tau over 2. This is a certain gain. I mentioned already there is no broadening. And this is your question, addresses your question. If there is an atomic velocity distribution from the beam, it means it of course leads to a distribution in the interaction time. So this, if we think of it as a function of delta, this t is not a constant if there is a velocity distribution. But it doesn't matter so much because we are interested in the central resonance, where delta is 0. So at that point, the t does not matter. So the central fringe is not influenced by the velocity distribution, but all the higher order fringes are. So the next fringe is of course the one where this cosine term goes to pi, then the square is again the maximum, and this corresponds to some condition, some detuning for a given interaction time, but if the interaction time is a distribution, then this detuning will not be fixed. And you can see this in this comparison. So these are two beam clocks, these are signals from two beam clocks. This one is with a velocity selection. You see many of those fringes, and this one is without a velocity selection with a full Maxwell-Boltzmann distribution from the beam. And you see that the central fringe persists, and the other fringes then are washed out very quickly. Both methods have advantages and disadvantages. So here, if there is no velocity selection, well, there is only one line, which is nice. If you see one resonance, you know it's the right one. And also, you don't have to do a velocity selection, so you can use a full flux of atoms. Here, this is the one that was built by PTB in the 1980s, and it was using this magnetic hexapole lens for the state selection that I showed you. And this lens, the imaging properties of this lens are of course velocity dependent. So it means that if this lens is used to image the atoms through the apparatus to some apertures or so, it will do a velocity selection, like it will select like a 10% or so window out of the Maxwell distribution, and then you get the very many fringes. It also has some advantages because the velocity also enters into some shifts, and here it is more easy to evaluate it. Okay, these are classical clocks. I'm now switching from the 1950s to the 1990s to go to the cold atoms and to go what we call the Cesium Fountain, and which is today's most precise cesium clocks based on cold atoms. The idea of the atomic fountain actually goes back to the 50s. Zacharias was a colleague of, like Ramsey, also they were assistant of Rabi in Cambridge, and he proposed to use a fountain, to use slow atoms, to lift them upwards under gravity, in order to realize Ramsey's scheme, but not with a beam flying in one direction, but with a beam going up and down. So I can show you on this slide already. So you have the atoms are thrown upwards, and then you want the two Ramsey interactions. You just have a small one microwave resonator. The atoms pass at 1 when they are launched. They are falling back under gravity, and they pass a second time when they come down. Great idea already for the 50s, and then Zacharias thought it would be possible just taking an atomic beam oven and pointing it upwards. He was doing, I think at MIT, he was doing the experiment. He had like a laboratory 10 meters high. He mounted a vacuum chamber 10 meters, and he figured that he would use just the tail of slow atoms from the Maxwell-Boltzmann distribution. And they tried, I think, for several years. They built several clocks. They never observed a signal. It was a failure, but an important failure nevertheless. Finally, the explanation of the failure of the experiment is relatively simple. The atoms from the oven have to pass through a nozzle, and in passing through the nozzle, the slow atoms are perturbed by the fast ones. So by collisions. So the the flux of slow atoms is lower than one would expect. They're just pushed away by the fast atoms, and that made this experiment a failure. But it was well known. It was in Ramsey's book. He explained it, and so Steve Chu, in 1989, immediately when cold atoms were available, he did a proof of principle experiment with sodium, and immediately showing that with cold atoms it was easy to operate. And then André Clairon and Christophe Salomon in Paris in 1991, in the early 1990s, started work on a serious metrological version of this using cold cesium atoms. And this is a picture of the first one that was built at PTB in Braunschweig. It's Stefan Weyers here. So this was the first one in 1999 that was operative here. You can see now again a 1 meter vacuum system with magnetic shielding, now about 1 meter high for the launching of the atoms. I come back to this slide, and it shows some lucky coincidence that cesium was a nice atom in the 1950-50 perspective. It also turned out to be a really nice atom from the 1995 perspective. A number of the early experiments on cooling and trapping were done with cesium, so it is one of the atoms that is relatively favorable for trapping and cooling. One can use set up a magneto-optic trap, optical molasses. Temperatures are very low. One has the sub-Doppler temperatures. It's easy to detect. Now we will not use a hard wire detector anymore, but of course using lasers. There is this strong resonance line at 850 nanometers. Already in the 90s, very efficient laser diodes on this line were available. And quite important, also the sub-Doppler cooling works efficient. The atom is heavy. The recoil velocity is low. That is a transverse spread of the atoms is small. And this is important because in the fountain, the atoms are thrown upwards. They are in free flight for like 1 second. And of course, they are still spreading transversely. And if they would spread too much, the atoms would have a small probability of falling back through the same microwave, through the hole in the microwave cavity on the second passage. And that's why it is important that the cesium recoil is only a few millimeters per second for the efficiency of the fountain. A new problem arose, which was not on the list and which nobody expected, that the cesium is a little bit of a problem for cold collisions. There is a bound state close to the continuum, so there is a relatively strong long-range interaction between cold cesium. They are flying in this fountain like for 1 second with a very small relative velocity, and so in the fountains it was discovered that there is a density-dependent shift of the frequency from this interaction, and so this had to be taken into account as an additional factor, which is about the little bit of drawback from the cesium. Okay, I can go quickly on this slide. Of course, you have seen this scheme. The state preparation is now done, of course, not with the magnetics, but with optical pumping. So for the cooling, the closed transition F equals 4 to 5 is driven, and then in order to prepare all the atoms in one hyperfine state, one can just switch off the repumper. Then one would do hyperfine pumping into F equals 3, and then driving the transitions from 3 to 4, and then detecting the 4 atoms in the fluorescence. This shows the overall sequence of operation of such a fountain clock. It is a temporal sequence, so atoms are loaded in an optical trap, in an optical molasses. Then they are launched against gravity. So this is done again with a moving molasses. So the two in this configuration, just the two laser beams that run vertically if a small frequency difference is introduced between the two beams, so that the atoms receive a start velocity of about 4 meters per second, so that they are launched by about 1 meter. And then on the flight, they pass microwave cavity first, fall down, pass second time, and are detected with lasers. This is a cut through the apparatus. You see the preparation zone, the detection zone. Then there is still a state selection to select atoms in the M0 sublevels, the Ramsey cavity for the interaction, and the free flight in a magnetically shielded environment with several layers of magnetic shielding. This is the Ramsey fringes you obtain from such a device. It looks like from the textbook, I would say, but it is a result of an experiment. It took a few hours to record. So each dot, each point, is one launch of about 1 million atoms, then so each point provides a signal to noise ratio of about 1,000 in 1 second. So that's the noise you see here. And then, of course, this is with a nice stable microwave source. So the microwave is stepped here, and I don't know, maybe 100 millihertz or so steps, and one can follow these fringes. This is the enlarged view of the central region here with the central fringe at 0. So here it just looks like a cosine term. You don't see the envelope very much. And now, since the velocity distribution is very well defined from the cold atoms, you can see the very many fringes extending into the wings of the pattern. The white area that you see here, so there's a little bit of loss. You see a little bit of loss of contrast here, and this is in fact due to the residual temperature that you have. So the height of this white area is an indication of the temperature. It looks so nice because people spend really time to make everything operate stable, to have the laser intensity stable, to have the atom flux stable, and so on. And it is quite important because I mentioned in the beginning, or I just gave you the number that the uncertainty of this clock would be 10 to the minus 16, the relative uncertainty. That is relative to 10 gigahertz. This is in the microhertz range, but the line width here is still 1 hertz. So in order to get to this microhertz, one really has to split this line by a factor 1 million, and this takes time. This takes averaging, so you cannot do it in a single experiment. So, but it's of course important. So you have this signal to noise ratio of 1,000 in a single shot. It means that in 1 second the instability is about 10 to the minus 13 thousandths of 1 hertz relative to the 10 gigahertz. And then to go down from 10 to the minus 13 to 10 to the minus 16, it goes like the square root of the number of measurements. Measurements are independent. So it takes about 10 to the 6 measurements. And 10 to the 6 measurements of 1 second, that's a few days. So one day is roughly 100,000 seconds. So it requires a few days of averaging to split the central fringe, and that's why signal to noise is such an important consideration. Please.
Are you actually locking on the maximum?
No.
Those peaks are on the side, so you get a better average.
Yeah, of course, very important consideration. Of course, the lock is on the side of the fringes. This picture is when the fountain is done to characterize a fountain. So it is done maybe once a year or so that we take this spectrum. The operation of the clock is that, of course, one likes to exploit the range where the slope is maximum. That is the frequency is stepped alternately from this point to this point, and then the population difference between these 2 points is measured and is taken as a signal to steer the oscillator. So there's no spectrum taken, but just a square wave frequency modulation. Yeah, another thing one may ask if looking at this picture, oh wow, how does it, but that's really tough. How can you be sure that you're locking on this fringe and not on this one? But that's not so much of a concern, because you see the distance. The distance is like a hertz or 2 hertz. So locking to the wrong fringe introduces an error of 10 to the minus 9, whereas the instability is 10 to the minus 30. And so this can be seen immediately within a few seconds that you are on the wrong fringe, and then you could go to the main fringe. Other questions at this point, please?
So, in NMR, there is something like this dynamical decoupling where you have a false phase. Would this make sense in this scenario?
No, such things are not used here. You're referring to dynamic decoupling in order to get rid of fluctuations of the magnetic field or something. Yeah, no, clock people do not do, or in this type of clock it is not done, because such a method they may be practically very helpful in order to reduce broadenings and so on, but they always come at the cost of increased averaging time. So in a dynamic decoupling scenario, I don't know if you know the term. So some perturbation would be modulated basically, and then some averaging would be performed. But it means that if you have a perturbation and you need to average, that you have to take some spectroscopic information which does not correspond to the optimum interrogation conditions. And here the criterion is rather to make the system as insensitive as possible, and then to always measure at the good conditions. So considering magnetic fields, of course, the protection against fluctuations of magnetic field is here to use the 0 to 0 component, which has no linear shift, and then to put this in a well-engineered 3-layer magnetic shielding, and then this provides the insensitivity.
So from the picture, it looks like a lot of atoms will be lost.
Yes.
Not really actual again.
That's true. Yes. So in fact, I was mentioning that it was important that the recoil velocity is small. So over 1 second, the molasses still spreads like 1 centimeter, and there is a constraint here for this cavity. So this is a microwave cavity that should be resonant at the 9 gigahertz cesium frequency. 9 gigahertz means 3 centimeters, 3 centimeters wavelength. And so this cavity should be relatively high Q. It should be closed for the microwave. You cannot drill a very big hole into it. Then the microwave leakage would leak out, which would be rather bad, because it would spoil the Ramsey method. The Ramsey method, you only want to excite the atoms at 2 well-defined points. If the microwave would leak out here, you would drive atoms all over this region, and it would make a perturbation of the line shape. And now the hole, is it big or small, of course depends on the wavelengths, and so it means if you have 3 centimeter wavelengths, the hole maximally can be maybe, what people use is 9 millimeters diameter of the hole. And then in addition you see there is a tube, we call this cutoff tube. So this is just a cylindrical disc that's resonant to the 9 gigahertz, and then there's a few centimeters of tube which also damps the microwave that tries to leave so it's like a waveguide that is sub-wavelengths. Okay, I'm explaining this to show that the tube has to be small, and that's why a significant fraction of the atoms are actually lost. Well, this is an artist's conception, of course, but it's not completely unrealistic that it spreads to a few centimeters. More questions? Please.
This fundamental connectivity that you were mentioning, is it fundamentally the basis of the system, or is it
It is a combination of a number of contributions, and I will go in the following, or tomorrow I will go through a number of the contributions for the optical clocks. I will not do the same type of analysis for the cesium clock. It is like 10 contributions that come together. One important one that was worrying the people was this collisional interaction, which is controlled by varying the density of the atoms. And another one that is now worrying people is problems of the phase of the microwave inside the cavity. When I introduced Ramsey method, I said it was very important to have a well-defined phase of the atoms. You see in this expression there is only just a detuning and then interaction time, but no phase of the microwave. But of course, in a real condition, the atoms may be seeing the microwave fields at different positions in space, and if one would have had to phase term, it would turn out to be blurring these lines. And even in the cavity, it's basically a standing wave cavity, but there may be some losses on the wall which introduce some phase differences, and these contribute to the uncertainties.
Just a quick question. Like, could be then a couple of decades, atoms could be changed to find a second?
Oh yes, that will happen with the optical clocks, and I will show you some of the candidates. But I expect indeed, as you say, it will take several more years, several decades. Okay, now you understand this picture, I think, better and in detail. This is again optical. I explained now in the microwave, oscillator, coherent superposition, Ramsey method, state detection, and so on. A few more details about this. So what's important here, that is, we call it an atomic clock. It really relies on a macroscopic oscillator that reproduces the atomic oscillation. So there is this closed servo system with a laser and the atoms, or in the cesium clock with a quartz oscillator and the atoms. And this is practically important because from this point on we have a macroscopic signal that we can use to develop further, to amplify, to distribute, to put on a radio station, and so on. We don't have, at this point, we do not have to worry so much about quantum noise and quantum mechanics anymore that we have to do here. So we have a macroscopic reproduction of the atomic oscillation. And this is why people call it a passive clock. So the atoms, passive referred to the atoms, so the atoms are not oscillating themselves, but they are driven by the oscillator. There is also some active clocks. The most prominent is a hydrogen maser, where there is an atomic population inversion is actually created. These atoms put into a resonator, and they really oscillate at their own frequency. They emit a wave at a low power, and this is called an active clock. But it has some problems. It is also, especially the hydrogen maser, turned out to be not as stable as a cesium clock. That's why cesium was used for the definition of the SI second. It's quite an important criterion here that really a coherent superposition of the atomic level is created. This is not kind of spectroscopy experiment where one would measure simple an absorption through a vapor or so. It is really essential that we have a coherence. You've seen Ramsey, this Ramsey scheme. You can only understand if there is an atomic coherence, and this is why sometimes people are speaking a bit widely about atomic clocks. I think this is one criterion that defines an atomic clock. Of course, it also means that an atomic clock is really a quantum device. Now, people speak about quantum technology with respect to entanglement and things. This is quantum technology 1.0 from the 1950s, but it is definitely quantum technology. It would not work without being quantum. And another practical thing that is also common to all kinds of clocks, it always runs in a pulsed fashion. So I explained it for the fountain, but it's also true for the optical clocks. So there is preparation, interrogation, and readout on the atoms. Yes?
Does this mean, in principle, do you need then two optical clocks to be sure to get a continuous, like, tick? Or do you just rely, or somehow that the microwave is on the same frequency until you get the next.
Yes, the second is a practical solution. So you need some intrinsic stabilization of the oscillator. You need some flywheel that helps you go over these over the dark periods where you do not see the atoms. That is what is practically if you just want to build one device. Of course, your first proposal is also would perfectly make sense. It would improve the stability if you basically you would also have the 2 times the signal, 2 times the atom number. But of course, it would be just 2 times as expensive. You would have to build 2 apparatus. But that's something that is actually considered or that is important to combine different signals.
Okay, then I think then the principal mechanism which makes this much better is the velocity selection somehow. Because in principle you could just make it vertically, or in a horizontal line, and then you could make like continuous operation of the clock.
It's not.
You could make like a very good velocity selection.
Yeah, but no, it's not only the velocity selection. It's also the cooling. It's a slow velocity because it is the cold atoms give you throw them up 1 meter. So you have the 1 second interaction time, which gives you the 1 Hertz line. If you would do it with a thermal beam, it would have to be 100 meters long. So that is just not practical. It's also the lines I showed you the Ramsey fringes from the thermal beam clocks. They were like 100 Hertz wide, and this is 1 Hertz. So that's an important gain. Oh yeah, this is something a bit more technical before going to the I think we are now prepared basically to go to the optical clocks. But I need to be, this is a little bit of a technical thing, a little bit about vocabulary. We are speaking about these great clocks, and I like to introduce the specifications that describes the quality of a clock. And they are called stability and accuracy. And you will hear me talking about this a lot, and so I should define these things. And I think it's also concept that is useful to understand for other types of measurement. Very simple. So stability, or here it's unstable, accuracy, inaccurate. So this is the output of different clocks or frequency standards over time. So this is frequency, this is measurement time. You look at this, and the dotted line is the reference frequency that you want to have. Say you want to have a 10 megahertz oscillator, it would be here. This is the output of the device. What is this? This is bad. So it fluctuates and it is off. So it is unstable and inaccurate. Stability, where stability describes obviously the fluctuations or the absence of fluctuations in the signal, and accuracy describes the agreement of the output with a nominal value. So this is something unstable and inaccurately it's useless. Where do I continue? I continue here. So this is an output that is stable over time, but it has an offset. It is stable but inaccurate. It may be useful because if you can measure this offset, and if it is really stable, if you know that tomorrow it's going to be the same value and the day after it's going to be the same value, then you can just correct it. So this may be a useful reference. You can calibrate it, and that's, for example, the case for the hydrogen masers. They may have an offset, but it's quite stable. This is the other thing. So this one here agrees on average with the nominal frequency, so it is accurate, but it has fluctuations, so it's unstable. So it is kind of problematic because you need longer measurement times and longer evaluation to find the value. But then in the end, if you spend enough time, you know that you find the right value. And this is what you practically encounter most of the time. And this is like the ideal, the ideal clock. It would be stable and at the right frequency. And for the stability analysis, so the accuracy, this offset is what I've described in this relative uncertainty, 10 to the minus 16 and so on. the stability, for the stability analysis, people are using something that's called the Ln deviation, and I'd like to briefly introduce it because it's really practically quite useful. The problem here is you want to make a statistical statement on a sequence of measurements that span a long time. So for time measurements, I've set you the cesium clock. It takes averaging like over 3 days, and you are measuring a value each second. So you have a long data set that may develop in time, and this Mr. Allen here asks the question how to treat it in a statistically reasonable way. And of course, in statistics, what you would do usually very often is you would look at the variance, but the variance may not be so useful to these long temporal sequences. For example, if the clock has a drift, then the variance of frequency measurements may just will not be a peak distribution, but a distribution that will just be broader and broader if you measure longer and longer, and so moments like variance will diverge. And this is a very simple solution to this problem is not to take the variance of all measurements, but of the two sample variance. So frequencies are measured, intervals k, and then the differences between adjacent measurements are done and calculate the variance of these ones. So in statistics, it's well known as a two sample variance, but this Mr. Allen, David Allen from NIST introduced this in the 1950s for the control of time and frequency measurements, and since it became so popular, people in the timing field call it the Allen variance. And then what people plot is they plot a double logarithmic plot of this variance as a function of the measurement time of the time that these frequencies intervals are used. And then this kind of diagram is quite useful for analyzing the properties of the clock. If you go to some conference on atomic clocks, basically in every talk you will see one or two such Ln deviation diagrams, and people will explain how good their clock is or where problems are with this clock. Yes?
Sorry, just to be clear, so is Allen variance a new time step independent of the previous time step? Or does it like update?
It is so frequency measurement are done at fixed time intervals, and then it just looks at the difference between two adjacent measurements. No updating over the previous history. There's some bad connection here. Okay, and what people are then reading off from this type of diagram is that so normally, of course, one would expect that in a good clock, this variance averages down with the measurement time. That's what you would like to have in a stability. The uncertainty should go down, but it depends on the noise, and there's a direct correlation between the type of noise of the clock, the spectrum of the dominant noise source, and the slope in this graph. And in a simple theoretical model, one models the noise as a function of frequency to some power, and then this power exponent here appears in correlation with the slope of this graph. And this is useful to distinguish different types of noise. So for example, if there is what people call white noise, no spectral dependence, which is common, which is shot noise or so, alpha 0 means that the exponent here, where's alpha 0, is minus 1/2. So the this Ln deviation improves like 1 over the square root of the measurement time. This is white noise. Bigger exponents here are related to phase noise. So this is white frequency noise. Phase noise leads to these higher exponents. They usually appear at shorter averaging times, and then they lead to a bigger slope here. The other important thing is so-called flicker noise. It has a 1 over f spectrum, so it increases towards lower frequency. And this is also something that appears practically quite often. For example, thermal noise sometimes has these 1 over f components. It just means that lower noise is more frequent at lower frequency, or it means that if you wait for a longer time, there is some averaging, but also you see rare excursions that go a longer way. And then in the averaging you do not gain anymore, but the exponent here -1 corresponds to a slope of 0 in this Ln deviation plot.
Short conceptual problem. Is it possible that the definition of tau is somewhat different for your example than, for example, if you want to measure like the line width of a laser? Because what you mentioned before was you kind of make 2 measurements and you see how they deviate, and later time you do that again. I wouldn't see why you would see such a profile though.
So
I would expect a flat.
So tau here, I'm using tau in somewhat different contexts. I'm sorry, there's not so much, not so many variables. So here tau denotes the duration. Is it written here? Yeah. It's not really written. Here. It denotes the duration of the elementary time interval that is measured. And so basically, what you do practically, you set up your counter or so, and you choose the smallest tau that you would like to analyze, and then you have this data set, and then you can just by calculating, then you can sum these bins and do the same analysis at 2 tau, 3 tau, 4 tau, and so on, and then this is the way people calculate these plots. It's done on a logarithmic scale, because in practice people really have to look from, say, 1 second to 1 month or so. So it spans a wide range of time. Okay, this was a little bit of formalism, but these diagrams you will see. This is just showing some typical curves of these Ln deviation curves. Log plot, the Ln deviation log scale. The tau in seconds, mentioned from 1 to 10 to the 7. Good clocks, most good clocks, they are dominated here by the atomic shot noise. So they average down like 1 over square root tau. Practical clocks always, sometimes have curves like this. So they average down for some time, and then they become flat, and then for long times they are running away. So this may be a clock that is dependent on some environmental conditions, say, for example, long-term changes in temperature or in magnetic field or so. Most commercial devices will behave like this, but what you would like ideally in the lab should be something that goes down like 1 over square root. Masers sometimes have the more strong slope at the low times. Okay, during the further lectures, you will see a few more of these plots, and that's why this is just to a remark, because even if you're not measuring time, you may find time or frequency. You may find this concept of the Ln deviation quite useful. It is used really in a number of concepts. So if you may have problems, I don't know, with the magnetic field in your laboratory, and you see it's drifting. It's not the same tomorrow as today. And a type of measurement like this, you do a sequence of measurements, and then you do this kind of analysis. May provide you some important information on where perturbations are. You may see where the curve starts to move up, or you may see if you have a periodic perturbation, you may see a maximum. Well, it's quite useful. And there is freeware software now available where you can simply calculate these variances. This is given here for download. and quite useful in a number of applications. This equation also is quite important. It shows the instability of a clock as a function of the most important input parameters. I do not derive it here. It's not completely rigorous. There are some factors in front, but it contains the important dependencies. The Ln deviation is given by the ratio of the line width to the frequency, which is what people also call the quality factor of the resonance, and then by a factor that basically measures the signal to noise ratio. So it is the cycle time of the interrogation and the number of atoms under the square root. So this is basically how and then divide the cycle time divided by the total measurement time. This is basically how many measurements are done. The single shot, signal to noise, and how many measurements are done. And from this equation you can see the importance of the higher operating frequency of the optical clock, to which I will come tomorrow mainly. You see that here in front the operating frequency is like 1 over this frequency. So if we go from the microwave to optical, the operating frequency is increased like by 5 orders of magnitude, and it directly enters proportionally into this instability. And this is an enormous gain. It is so big that you can afford a reduction of the atom number. I've told you that in the Cesium Fountain there is maybe like 10 to the 6 atoms. But if we're going from the microwave to optical, we win 5 orders of magnitude. We may in principle even go from 10 to the 6 atoms to 1 atom, and we are losing 3 orders of magnitude. So a single atom interrogated in the optical gives a better stability than this ensemble of 1 million atoms in the microwave. And of course, you may still want to interrogate 1 million atoms in the optical, but just to show you the enormous potential of the optical clock, and that's actually something that was behind the early proposals to really use a single particle, and that's actually one of the clocks of the optical clocks that are used working with single particles. It is possible. It provides a significant, it still provides an improved uncertainty. The other important advantage of going optical is that some of the perturbations, I've spoken about collisions, some of the perturbations have an absolute energy scale. Also perturbations in direction of the atom with the magnetic field. It more or less has an absolute energy scale that is determined by the magnetic moment and the magnetic field. And if you take the energy change as a perturbation in frequency, of course the relative influence on the higher frequency is less. Simple criterion. So again, an optical clock has an advantage over a microwave clock. And this is just comparing for 2 examples the relative shifts, for example, from the quadratic Zeeman shift at 1 microtesla. It is about 10 to the minus 12 at the microwave clock, about 10 to the minus 18 at the optical clock. Quadratic Zeeman is due to you've seen the level diagram of the different levels. We are working on the 0 to 0 components, but going to high field, of course, the lines somehow have to curve, as I've shown you, and this curvature somehow already sets in at low frequencies, and that's why a quadratic Zeeman effect has to be taken into account. Blackbody Stark shift from room temperature electric fields, again significantly lower on the optical frequency than on the microwave frequency. So this is the improvement in the in the accuracy, in the sensitivity to perturbations. It does not hold for everything, because some shifts are just proportional to the frequency. And the most important is the relativistic second order Doppler effect. This is time dilation, the change of time in a moving system. First order Doppler effect, frequency change V over C. Second order Doppler effect, V square over C square. And this is just a factor, so the delta nu over nu is just given by V square over C square. So it is going to the higher frequency, the shift will also be higher. But it is V square, so it is related to the kinetic energy, so it is related to the temperature. So this is something where cooling is important. So only cooling helps to reduce this type of shift. And we put in some numbers. Say a 1 millikelvin temperature that's easily obtainable with laser cooling, a middle mass atom with 100 atomic mass units. You put into this equation, delta nu over nu is 5 times 10 to the minus 19. So cooling 1 millikelvin gets rid of this effect. So combination of optical and clock and cooling has to go together. But now I'm talking second order Doppler effect. What about the first order Doppler effect? So even at this 1 millikelvin temperature, the V over C would still be like 10 to the minus 10. Just putting in the numbers. So if you would multiply 10 to the minus 10 by the frequency, that would be an enormous shift. In the optical, it would be a kilohertz shift. So how to build a 10 to the minus 18 clock if one would have a 10 to the minus 10 shift? No way, it would not be possible. So the Doppler shift, so the first order Doppler shift has to be really eliminated, and it is eliminated not only by cooling but by the localization of the atoms. That is what's that is what is, I'm sorry about it, that is what is called the Lambdicke regime, to localize the atoms on the scale of the optical wavelengths. You have heard yesterday already about Dicke superradiance, and this is a related concept about the localization of the atoms. But since it is quite an important concept, I think I should reserve it for tomorrow. I'm running out of time, yeah. And maybe at this point ask if there are further questions at this stage.
For the Ln Deviation, what are the assumptions in the guidance logic that you're using?
Where was it? Sorry, this one. The assumptions are that so that there is a spectral line profile of this width and this frequency, that it is interrogated alternately in the wings of the line, as I've explained for the cesium clock, and that the noise is determined by the atomic shot noise, or by the quantum projection noise. It's also something I'm going to explain in the second lecture. So we expect an absence of technical noise like laser noise or so, oscillator noise. Is not included here, so it assumes that the oscillator is already stabilized on short times to something like a line width that is smaller than this, and that the atomic signal is used for the long-term steering of the laser, and that this is the atomic shot noise also that limits the signal to noise, and that's why here it just enters the number of atoms and the number of measurements. So the total measurement time divided by the cycle time. And then if one does the more rigorous deviation, that's why I put the approximately here, there will be a numerical factor in front of this of order of unity 1. And this factor will depend on the details of the servo, like in which way it is interrogated, which type of spectroscopy, what type of temporal overhead, and so there will be additional factors in front. Is it
Two slides before you showed this last talk on the coordinate, the Ln deviation and its dependence on the different types of noise. So does it mean that I guess not all of these noises are technically equal, right? You would have like an interrogation time of 1 second. Does it mean that white phase noise would be worse than flicker noise, or is that not true?
Again, it is not the interrogation time. I'm sorry for using the tau multiple times. So this is already the measurement, the time that the oscillator is followed. So typically the interrogation time typically is shorter than the tau, so that one would already start at a few averages over atomic interrogations. But what you're saying, I think one aspect is that different noise sources typically contribute on different time scales. So on short times, the phase noise issues is typically associated with properties of the oscillator. So for example, if you think about a laser oscillator, the dominant problem is the shaking of the mirrors. That pull the laser the frequency, and this typically, if the shaking of the mirrors is just a small fraction of the wavelength, then this typically can be described by phase noise, and then it would be thermally or it would be white depending on the acoustic conditions. So on the short time, one dominantly has phase noise contributions, and then there is this regime where there is the shot noise dominating, which is normally the dominant regime in measurement times. And then at long times, this is drawn typically like this, at long times one comes at this flicker floor where there is some fluctuating things, or if things are starting to drift, then or a random walk, noise in the frequency, then the curve would go up again. But how it really looks over this wide range of timescales really depends on a number of parameters of the oscillator, of the clock setup, of the laboratory environment, or so on. It is hard to predict in detail, and that's why these type of curves is so valuable for the diagnosis. So one takes these and looks at them and sees, aha, here's a problem that we have to address. Not necessarily. Yes, in one may, but yeah.
So meaning that both instruments like sub-brilliant states to increase the accuracy or the coherence time, the excitation.
Sorry, what type of states?
Sub-brilliant states. So like collective states that
Ah.
have from a lifetime. And so my question is like previously I was talking about the frequency of the individual atoms, or because this collective states have shifted frequency.
Exactly. Yeah.
But should we then measure the frequency of this new collective states, or
You gave part of the answer already. Yes, it could be some advantage to measure collective frequencies in the term of you mentioned the term of more narrow line widths. But there's a strong disadvantage is that this type of clock it may provide a very good stability, but maybe not such a good accuracy. And so I'm the guy from the fundamental metrology. So we want to realize like the unit, and this is, you want to keep as universal as properties as possible. So you would like to say, take this hyperfine transition in the cesium, and not explain anymore, like how many cesium atoms under which conditions. So everything is idealized, is taken away. And if you would go to something like a collective property, you would have to start describing these conditions, say how many atoms at which density, at which energy, and so on. It may have some advantages, but it would lose this universal character. And that's why for these fundamental clocks we always try to have the idealized isolated atom. And one ideal is really the single ion that I will speak about tomorrow, or even if we speak or for neutral atoms, we always are speaking about rather dilute vapors, so without these collective interactions.
The accuracy, the stability would increase, but the accuracy would decrease. But
exactly. That's right. Then that's a likely outcome. And the parameter you were mentioning, like getting a narrower line width, there may be a choice. One can just, even in an isolated atom, you can select very narrow line widths by just selecting transitions that are linked to long-lived metastable levels. And there is a wide range. You may think of excited states, 100 seconds or so, that are much narrower. So the natural line width is much narrower than we can obtain with lasers today. So it's not a limitation of the line width.
Let's stop here. Thank you.
Thank you.